So these next ones, just in the interest of time, I'm going to just do quickly on screen, and hopefully you can follow it. Just keep in mind that the things with 5, it's not possible to just multiply it by itself, because all that becomes is squared, and the square cannot get rid of the 5. So in this case, I would have to multiply. Well, I could probably simplify it. There's a number, for instance, 2. I believe it's possible. For instance, 2. I think we did this one. 2 times 81, for instance. And the 5 root of 81 is, I think it was 2 we discovered. So you can just do to the power of 0.2. That's the same as 5 root. No, it's not. So maybe try 162. Maybe 162 has a 5 root. And to the power of 0.2. No, it does not. So let's see what 2 is. Anyway, 2. That's the power 3, 4, 5. So 32. So let's see if 32 can go into 162. No, it can't. And I imagine, no, probably not 6. So we'll just do it the hard way. So what we need to do is we need to multiply it by 4 of these. 1, 2, 3, 4. And if I multiply it by the bottom, it's essentially that to the power of 4. And if I multiply it by the bottom, I have to multiply it by the top. On the bottom, what happens is it becomes to the power of 5 because there's already 1 there. And that power of 5 cancels out with this power of 5, which essentially gets rid of the root. And 3 times 162 becomes 180, 300, 486 at the bottom. Up top, this 2 root cannot go into there because this is to the power of, actually, yeah, I think it can actually, because the 4 can't just go in as a 2 though. Well, no, I think it can't, because this square root, 5 root to the power 4 is the same as this, times this, times this, times this, which means you could multiply each number by itself, like this, 2 times that, times that, times that, times that. You'll probably get a huge number. Now, it would be good to know some classic 5 roots, like 3 times, or 3 to the power of 5. 243, just so that we can spot some of them, then maybe they exist. But let's find out what 162 to the power of 4 is. Times 2. What's that? That many million. So, I mean, I guess you could see if, let's see, it ends in a 2. Let's put it in memory. Let's divide it by brackets. 2 to the power of 5. Yeah, okay. So it's got that in there. Let's see if 8 to the power of 5 is doable. We'll do a little trickery here. No, it's not. So, I mean, 2 to the power of 5 is in there. It's dividable up there. So I have no doubt we could simplify it. There's probably a trick I'm missing here right in the beginning for simplification purposes. There's probably a way to get the 5 root of 2 out of the 162 so that we just cancel it. Actually, there is a simpler. Of course I can. This is the same as yeah, of course I can. My mistake. 81, even though 81 does not have a 5 root. But this is the same thing, which means I can replace it. Which means this cancels with that, and I'm left with this. But to get rid of this 5 root, I have to multiply it by 5 root to the power of 4. And that means top and bottom. And down here, it will just become that. Up here, it will just become that. And this essentially will just cancel at the root. So I'm left with 3 times 81, which is, as we did before, was 243. Now, one of the smallest 5 roots, 2 to the power of, well, I should say, yeah, 2 to the power of 4. Can this be simplified? Does 81 to the power of 4 have a power of 4 have a 5 root? No, it doesn't. But we should again learn some of the basic 5 roots, like 4, power 0.2, or rather 4 times 4, 4 to the power of 5, 1044. And we should see if it's in there. Where's the clear? So 81 to the power of 4. 4. See if that's divisible by 1024. And it's not. So it's made our life a little tougher. Especially this 4 to the power of 5 thing. Because there are some numbers at power 4 that would have a 5 root. Not easy to figure out like this. So maybe there was another trick in there. But I don't think so. Let's just pause this for a second. Okay, yeah, there is a way. So if I look at the 81 in here, 81 is the same as 3 to the power of, let's see, 3 times 1, that's squared, cubed to the 4. So we got, and this 4 power out here can be put in there. So we got 3 to the 4 to the 4. 3 to the power of 4 to the 4 is the same as 81 to the power of 4. It's the same as 3 to the 16. Now the secret to working with any root is if this is a 5, you got to find the number up here that can be divisible by 5. And the lowest number that can be is 15. So that's the same as 3 to the power of 15 times 3 to the power of 1. Which means this 81 to the power of 4 can be replaced with this inside. Well, these can both be rewritten like this. 3 to the 15 over 5 times 3 to the 1 over 5. This is always the power. This is always the root. This is clearly can be simplified to 3. And 3 to the power of 3 is 27. So this becomes 27 times the 5 root of 3. The only question that remains is, can 27 be divisible into 243? Probably can be. Or some simplification of it. 9, yeah. So that means this cancels out, and this becomes a 9. So we get 5 root of 3 over 9. Pretty tricky. Pretty tricky stuff, yeah. Might even be able to be simplified with the 9 a bit, but that's okay. Yeah, we'll just leave it like that. Yeah, that's some pretty tricky stuff. Not used to it. So really what they want us to do is express this as um, a exponent is our easiest way to do it. But we'll keep stumbling through it like this. To get rid of this, we have to multiply by two other versions of that. And if I do it at the bottom, I have to do it at the top. Down here, it simply becomes a 9. Because it's 3 root cubed. Up here, we should probably look at ways to simplify this. This, if I look at it, 3 root of 9 times 3 root of 9, the same as 3 root of 81. Three times the 3 root of 81 is this. And 3 root times that of 81 is 243. So we're back at that. We should quickly realize that 3 times 3 is 9, times 3 is 27, and times 3 is 81. So 81 here can be represented as 3 to the power of 4. So we'll leave this one the same. But this one here, when I look at the 3's, it becomes 3 to the power of 5. Right? This can be changed to 3 to the power of 5. This is easily proven by taking 3 and putting it to the power of 5. $243. Well, I'm looking for some component of 3 in there. So 3, and keep in mind 9's down here. So 3 cubed times 3 squared is 3 to the power of 5. So that means I'm looking at the cube root of that and the cube root of that. That's just 9. So that has an answer is 3. So this can be replaced as 3 times the cube root of 9. Okay. Actually, I think cube root of 81 might exist too. No, it doesn't. But 27 does have a cube root. Oops, 9 times 9, 3 times 3 times 3 is 27. And 27 times 3 is that, 81. So this also can be replaced as 3 cube root of 27 times cube root of 3. This cube root has an answer of 3. 3 times 3 is 9. So this here can be replaced as 9 cube root of 3. All over 9. Well, this can be simplified a little bit. This, if I, for instance, factor out a 3 from both of these, I get 3 here and nothing here. And then this 3 simplifies with this 9. Now, some of my arithmetic might have been wrong or too quick here. But so far what I have is 3 cube root of 3 plus the cube root of 9 over 3. Annoying, for sure. Yeah, that was the answer. It's annoying. It requires a lot of practice and understanding the difference between a cube root. So this, there's some simple steps we can take with this one first. First of all, notice that the cube root of any cube is simply whatever the base is. X up here as well. The cube root of y to the 3 is simply y. So that means you can simplify those before you even start. So the cube root, because you can do cube root of each of these individually. So that's out. And up here, this one's out. Just makes our life a little bit easier. You cannot, well, no, technically, keep in mind that cube roots of negative numbers exist. Technically, these can divide. No, they can't because there's a plus here. So we have to get rid of this radical. So we're going to multiply top and bottom by it. Okay. At the bottom, it simply disappears. That's why we're doing it. Oh, we have to do it twice. Yeah, twice because it's a cube root. So up here, I'll just essentially square it. You could do the distributive property too and put the square here and the square here. Doesn't really matter for now. Up here, by doing it, it simply disappears. And you get, we might want to just keep it like that for now because it's probably going to simplify. Up here, we have to do a distributive property. So you get -2 up top. You get -2 times the cube root of 15 squared and y squared. Or if you want, we'll just do it like this. That's -2x times that. Essentially, it's this. Plus y times that. All over this. Now, this has an x here and this has a y here. Doesn't let us cancel out. This y2 cannot be brought out because it's not bigger than a 3. And 15, unfortunately, doesn't have a root. 15 squared. $225. Let's see, 5. There's squared. There's cubed. No. $225. It doesn't really work. Yeah, there's a couple steps I missed, actually. But, again, these... Not sure if your teacher meant... I mean, meant to be this complicated. But, let's go back a little bit, Because I say that because the other questions are not like this. One thing I missed up here is this x to the 4. This x to the 4 can be expressed as x to the 3 times x to the 1. Which means we could have found the cube root of the x to the 3 and brought it out with the y. So this actually simplifies to this with an xy in front. Down here, no, I was right. Only this can be brought out. But the nice thing here is the x here and the x here can make my life a little simpler. And the X exists in both of them of something that's being added. You can get rid of it. And then I simply multiply by this squared. So you need two of them for a cube root, top and bottom. Down below, the cube root disappears. And I'm left with 3 times that. 3 times that is 45. Up top, you distribute minus 2 times that, which is probably going to be straightforward. And in here, you're allowed to multiply them individually. Minus 15, it's 15 squared times minus 5. Now, here's something I probably missed. This 15 squared is the same as 5 times 3 squared, which is the same as 5 squared times 3 squared. I'll just pull the y, so I just ignore the y. Let's talk about the 15. Well, when I reduce it to 5 squared times 3 squared, this minus 5 times 5 squared becomes minus 5 to the 3, which means I can then bring it out as a minus 5. That just leaves x and y in here with a 3 squared, which is 9. There's not much you can do about the 5 and the 2 because they don't go into 45. But as far as I can tell, that's probably the simpler form. Sort of needlessly difficult, these questions. We'll try to continue. What's the next one? Essentially, we're looking for things that can be multiples of whatever the root is. Okay, this one here. Right. So there's no easy visible 4 roots. Can't really get rid of them. So to get rid of this 4, we have to multiply by 3 versions of this. So essentially this as a root. As a 4 root. Cubed. Cubed. And the cube can apply to each thing. Or another way of seeing it is times itself 3 times. So down below, that just gets rid of it. Up above, it's this version, but cubed with a 3 in here. So that just means that this becomes 27k to the 9. K to the 9. Well, when I distribute it by the top, it becomes 3. 27k to the 9. And beware, we can come up with the power 4, and then it becomes minus. And these can multiply each other. 5 times 27 is 135. k2 times k to the 9. We add them, k to the 11. Now, it's possible to simplify the k's because the 9. K to the 9 is the same as k to the 1 times k to the 8. And if I separate k to the 8 with its own 4, it's k squared. So that just leaves 1k in there. Over here, for k to the 11, it's the same as k to the 8 times k to the 3. K to the 8 over 4 is k squared. Means I can pull a k squared out, and I'm left with a k to the 3 in there. All of it over 3k to the power 3. Well, I got k squared here, k squared here, k to the 3 here. So it can cancel these out. You got 4 root of 27k, which I don't think can be simplified. And here minus 4 root of 135k squared over 3k. The question is whether there's a multiple like 5 times 5 times 5 times 5. 25, 125, no. 625. So no. I think that's as simple as it gets. On to the other one. Hopefully these are a little bit easier. So you're allowed to subtract things that have the same root. So the secret here is going to be trying to make things have the same radical. Like 5 apples minus 2 apples is 3 apples. So they start you off with a simple one because these are the same root. So you can just pretend for a minute to ignore this part. Just bring it back later. What's minus 9 plus 10? 1. So it's 1 apple. Or just that. That's the answer. Minus 9 of them plus 10 of them is 1 of them. Pretty simple, right? This one, where there's something getting trickier, is saying, what's the common one number between 18, 8, and 24 that has a square root? Well, it'd be 4. Maybe not 8 for 18. It'd be 9 for 18. This one is 4. And this one's 4. And this one's 2. So minus 3. The 18 can be written as this. 9 times 2. And the y can be written as y to the 4. So 9 times 2. And the y can be written as y to the 4 times y to the 1. Because that adds up to 5. Well, that has a square root. It's y to the 2. And that has a square root. It's 3. And remember, this minus 3 is in front, so it's minus 3 times this 3. So it's 9, minus 9. And we're left with radical 2. So right there, that's the hint that I'm probably going to have to convert. Oh, radical 2y, because I had one y left in there. That's the hint that probably these two have to be converted to radical 2y. So again, it's simplified to minus 3 times the square root of 9. That's insanely huge. Times the square root of 9, which is 3. Times the square root of y to the 4, which is y to the 2. Minus 3 times 3 is minus 9. So minus 9y squared. And in the center, in the root, was 2 was left over, and y was left over. Like that. Once you kind of figure out the simple one, that's a hint to what the other ones need to become. So if I look at this one, for now, just ignore the 3 and say, well, the 8 can be converted to 4 times 2 and 4 has a square root of 2. So inside I'm left with the square root of 2y, which is what I want. And out here I have plus 6. So far I have minus y, 9y squared, plus 6 radical 2y. Not sure what I'm going to do with this y squared. And finally, this next one is 8 times 3. That's not going to do it. 24 doesn't have a square root. 4 has a square root. 4 times 6. And 6 has a square root of 3 times 2. Not sure what that's going to do. Anyway. Minus, so I'll just start with 4 times 6. 4 has a square root of 2. And square root of 6. And then y cubed can be represented as y squared times y to the 1. And y squared as a root. So I'm left with this. That's the only one that didn't really turn out the way I wanted to get a 2y. But I can't really add this to that anyway because of this y squared. These are no longer measurable terms. Yeah, this one's a weird example. I mean, you could technically group the 6 minus the 9y squared because you like to have positives first, and multiply it by the radical 2y, and then subtract 2y radical 6y. But that's about it. It doesn't really simplify. Well, it's a weird example. I'm not sure. Usually I like to see the point of what they're teaching. I'm not sure what the point was. Oh, that was a harder one. That was 8. So let's stick to easier ones. Okay, so this one, clearly they're the same radical. So what's minus 10 plus 10? It's 0. So the answer to this one's 0. Couple of easy ones here. Are they the same radical? Yes. So what's minus 3 minus 4? Minus 7. And then you put back the radical. So there's minus 7 of these apples. Okay. This one is where they start to teach you how to be tricky. You have to say, is there a number multiplied in here that I can get a square root out of? And yes, it's 9 times 3 is 27, which means I can replace 27 with 9 times 3. And the square root of 9, I can just rewrite the first term because it's as simple as it gets. The square root of 9 is 3. So we get 3 in front times the square root of 9, 3. Left over with the square root of 3. 3 times 3 is 9. So I get 9 square root of 3. Now these radicals are the same. Therefore, I just look at minus 2 plus 9. That is plus 7. So the answer is 7 apples. Okay, so these are, the baby steps. They're walking you through the baby steps. Okay, so number 5, mixed radical, and they're trying to teach you the tricks as you go. Okay, here you have to examine the 54 closely. 6 can't be simplified, so it's going to be 6 times something. And we discover that 6 times, let's see, 27 is 54. 27 times 2. And 27 is 3 times 9. So it's 6 times 9. There we go. And then the x to the 3 is the same as x squared. So this is 6 times 9. And then the x to the 3 can be simplified as x squared times x, which means the 9 can come out as a 3. The x squared can come out as an x. So you're left with 2. square root of 6x, plus 3 times 3, 9, x, square root of 6x. Now what's interesting here is x represents a number we don't know yet. Therefore, I cannot add it to the 2. Now you could write it like this. 2 plus 9x times square root of 6x. Most likely your teacher just wants you to keep it in this form. So 12 can be represented as 4 times 3. 4 can come out as a 2. Most likely we're looking for radical 3 over here. So you get minus, what's the square root of 4? 2. X squared y squared times the radical 3. And here the only thing that come out is y to the 4. The square root of y to the 4 is y to the 2. So you get plus 3x squared y to the 2 radical 3. And you cannot add these numbers because they're, oh, yes, you can. There's x squared, y squared. So it becomes 3 of these apples minus 2 plus 3, just 1. So it just becomes 1 of these apples. X squared, y squared times the radical 3. This can be simplified as 4 times 5, but this cannot be simplified. 4 times 5, the 4 can come out. 2 times 3, you can simplify this to 6 radical 5. But this one stays the same. It's the same as, yeah, not really. I say it's the same as radical 5 times radical 2, but then they can't be subtracted or added when they have 2 different radicals. Maybe your teacher's going for this. So you got 6 radical 5 and minus 5 radical 5 radical 2. So you could factor out a 5 in front, and you'd be left with open brackets 6 minus 5 radical 2. Possibly your teacher's going for that. Yeah, we already figured out 8. This is sort of a nightmare. So this one is 9 times 2. 9 comes out. It's a 3. 3 times 3 is 9. So you get 9 radical 2. This is 4 times 3. 4 comes out as a 2. So you get plus 6 radical 3. This 127 is 9 times 3. 3 comes out times the 2. So you get plus 6 radical 3. So because this is a radical 2 and this is a radical 3, only the radical 3's can be added up. You get 9 radical 2. And what's 6 plus 6? 12. 12 radical 3. That's the simplified answer to that. First one can't be simplified at all. Second one is 4 times 5 again. 4 times 5. The 4 can come out as a 2. So you get this first one stays the same. 2 times 5 is 10. There's nothing you can do about the radical 5. And this is 2 times 4. 4 comes out as a 2, so you get minus 6 times radical 2. Over here, minus 4, minus 6. So you get minus 10 radical 2. And generally speaking, we like to put the positive numbers first. So you get 10 radical 5 minus 10 radical 2. You could factor to 10. Radical 5 minus radical 2. I'm not quite sure why you do that, but some of these aren't making sense anyway. The first one has a factor of, I think it's 9 times 5. So the 3 can come out, and that's a minus 1 essentially. Get minus 3 radical 5. Plus 2 radical 5 can't be simplified. This is 4 times 5. 4 comes out as a minus 2 radical 5. Plus 2, and this one has the same one as this. It's 9 times 5. The 3 comes out. The 9 comes out as a 3. So you get plus 6 radical 5. These are all apples. So if you want plus 2 plus 6, 8. Minus 3 minus 2 minus 5, 3. The answer is 3 radical 5. Because they all had the same radicals. Wasn't too bad. So that was 11. And 13. Hopefully this is not an assignment. I'll be asking your supervisor if these are assignments or if these are tests. Because if I'm being asked to do assignments, the tutoring will stop. I'm only here to help you improve, not to do the homework. This is 3 times 9. The 9 comes out. Get minus 3 times radical 3. This doesn't really, it's 9 times 5. 3 comes out, so you get plus 6 radical 5. 4 times 5 minus 2 radical 5. And this is a, what is that one going to be? You get 4 times 20. Yeah, 20 is 4 times, so 16 times 5. 16 comes out as a 4, so 8 radical 5. So the 5s can be added. 6 plus 8 is 14, minus 2 is 12. So you get minus 3 radical 3 plus 12 radical 5. Generally speaking, we put the positives first, so it's 12 radical 5 minus 3 radical 3. 9 times 2, so this comes out as a minus 6 radical 2. 16 times 2, so this becomes a 4, so it becomes minus 16 radical 2. The 50 is 25 times 2, so it becomes minus 5 radical 2. And this becomes 4 times 2, so that becomes 12 radical 2. They're all radical 2s. This is only positive. So minus 6, minus 22, minus 27, plus 2, so you get minus 15 radical 2. Is the final answer. These are much easier than the last ones.